Hi, my name is Andrew Thomas, and I'm an undergraduate studying computer science. My topic is optimization of path selection for multidimensional robotic motion. So what is the motivation for planning motion? Right now, a big goal in robotics is to be able to issue high-level task instructions to robots and have them carried out successfully. To accomplish this, multidimensional autonomous navigation of the robot's drivetrains or other mechanisms such as robotic arms is a fundamental prerequisite. Mobile robots are being used in more and more complex scenarios, so higher levels of control and predictability of the exact motions the robots will take is becoming more and more important. When we plan the motion, we can account for more complex constraints such as extreme kinodynamics introduced by things like high loads, or interesting accelerational interdependencies introduced by the specific mechanical design of a mechanism. Additionally, when we plan motion, we can optimize the motions of the robots, which can relieve costs from domains like smoothness, which relates to passenger comfort or payload safety, the time of travel of the motion, and energy consumption. Applications. Path selection is relevant for any cyberphysical system that employs motion. I'll be focusing on WMRs, wheeled mobile robots, following two-dimensional paths. Two examples of WMRs are differential drive robots, also known as skid steer, and synchrodrive robots. Both of these robots are able to have both translational and angular velocities. Other applications examples are robotic arms following multidimensional paths. This is very relevant in the field of manufacturing. Although I'm focusing on path selection in this project, to optimize path selection, you really have to look at the other parts of the process for controlling motion in robots. This process involves three main steps. You start with path selection, then you do trajectory generation, and then there's the execution stage. In path selection, you select a path for motion based on waypoints you want a part of the robot to go through. This path doesn't encode any information on the velocities involved. It's just a understanding of the positions that a point on the robot will go through. Then you can go to trajectory generation, where you actually calculate the velocities, translational and angular, of the robot along the selected path. Finally, there's execution, where you have some kind of controller that attempts to exactly follow the trajectory. This might involve feedback controllers to account for real-time error. So starting with path selection. Paths are represented by splines, which in this context is defined as piecewise polynomial parametric curves, which pass through each of the waypoints. The segments of the splines are defined by the waypoints, such that for a given n waypoints, the resulting path has n-1 spline segments. Here's some examples of some generated splines. You can see they pass through each of the waypoints. For drivability, there's a couple of required properties. First of all, there has to be continuity in heading, which ensures that there are finite rotational accelerations throughout the path. This is c to the 1 continuity. Secondly, there has to be continuity in curvature, which ensures finite translational accelerations for real-world drivetrains, and then this implies c-squared continuity. Finally, the start, first, and second derivatives have to be controlled because they have to match up with the state of the robot at the beginning and the end of the motion. If your robot is stopped at the beginning, this implies that the first derivative points in the same direction as the robot, and the second derivative is 0. On top of the required properties for path planning, there's a couple desired properties that make optimization a lot easier. First of all, localism. This means that if we make a change at one segment of a spline, it only affects a bounded number of neighboring segments. Secondly, we want a correlation between the shape of the spline and its parameters. If there's a more intuitive relationship between the parameters and the shape of the spline, then any changes we make to certain parameters to optimize the path have more predictable effects on the overall shape. So the mechanism I decided to use for path selection is called quintic-Hermite interpolation. Basically, this is a mechanism that allows you to find a polynomial such that it has certain function values, first derivatives and second derivatives at the start and the end of the function that you specify. You end up with these 6 basis functions, which are fifth-order polynomials. You multiply them by your 6 parameters for the function values, first and second derivatives. You sum them, and you get a polynomial that has those first and second derivatives and function values. So for my spline generation, I wanted to be able to generate a spline based on only 3 things: the initial heading, the end heading, and a list of the waypoints. This leaves the first and second derivatives at each point in the spline to be determined. And we want to determine these in such a way that we get a good spline, where a good spline means that we distribute the changes in curvature along the segment to get a smooth spline. This is a compromise between the spline being taut around the waypoints or loose around the waypoints, which is sometimes called the spline's tension. To do this, I used a method for choosing tangents called Catmull-Rom, in which basically for a given waypoint, your first and second derivatives are determined by using the neighboring waypoints as control points. So your first derivative is the vector between the previous waypoint and the next waypoint divided by 2. And your second derivative is the vector between the previous waypoint's first derivative and the next waypoint's first derivative divided by 2. This gives you a pretty smooth curve. So this is what the actual code for that looks like. Basically, given an initial derivative value and a final derivative value and a list of values, we're able to determine all of the first derivatives, all of the second derivatives. We have all of the function values. Therefore, we can use all of those parameters to generate a quintic-Hermite spline. So this is what the code for generating the actual two-dimensional spline looks like. So we start with a start heading and an end heading and a list of two-dimensional points. And what we have to determine first is the start and end derivatives for both the x and the y splines. So basically how I determined this was I took the distance between the first and second points and then the final point and the second to last point. And then I took a vector in the direction of the start heading and the end heading and made its length half of those distances and used that vector as the start and end derivatives. So now with the path selected, the next step is to do trajectory generation. So we can generate a velocity profile for the path that was selected for a robot with a given maximum translational acceleration, maximum translational velocity, and maximum rotational acceleration constraints. So the process here is we first break the spline into a large number of equidistant planning points, as is depicted over here. Then we step forward in time from the start of the spline, and we determine the achievable velocities for each of these points based on those constraints mentioned, assuming a constant acceleration between the points. And this achieves forward consistency. Then we have to go back from the end of the spline, stepping backwards in time, using the same constraints to determine the achievable velocities. And we take the minimum of both the forwards stepping and backwards stepping, and then we get a fully constrained velocity versus distance profile for the path that our robot can follow because we followed the constraints. And the last step is just to reparameterize this solved velocity versus distance profile to be velocity versus time using basic kinematic equations. So how do we model these constraints? Well, translational acceleration is pretty simple. We can use v final squared equals v initial squared plus 2ad and find both an upper and a lower bound on the velocity at the current point based on the previous point's velocity and the distance in between those 2 points. Angular acceleration is a little bit more complex because we're trying to constrain translational velocity based on angular physics. So we can use the equation angular velocity equals translational velocity times curvature to mediate these 2 different domains. When we look at the constraint on change in angular velocity based on the angular acceleration and do some substitution with this equation, we can form a relationship between angular acceleration and the velocity, the translational velocities at the point and the previous point based on the curvatures, which are all known. However, this depends on time, so with a little more substitution, we can get this in terms of distance, which is this big inequality right here. That inequality describes one of these 6 parabolas. The top 3 are when the curvature is greater than 0, the bottom 3 for when the curvature is less than 0. The intersections are where either the maximum or the minimum angular acceleration are being used. There's one degenerate case when the curvature at the point is equal to 0. When we do some substitution, the inequality simplifies to this right here, which is a linear function whose bounds are these 2 points. So the solution set for the velocity, achievable velocity at a point, given an angular acceleration, the previous velocity, and the curvatures at both the current point and the previous point, looks like this. Based on these 2 constraints, we end up with 2 ranges of achievable velocities for a point based on the previous point's state. We want to take the maximum value that lies within both of these ranges, as this will minimize the time to travel the path. However, sometimes these two ranges don't match up. And in this case, we have to introduce a new constraint, which is a threshold on the previous point's velocity. To model this constraint, we can do a lot of algebra on the two different constraints to find a maximum velocity at the previous point that will guarantee that these two ranges overlap. That ends up being really, really ugly, and here's some of the code for that. But at the end of the day, we're able to constrain the previous velocity based on its value, based on the other two constraints and this new threshold, to guarantee that we will always have an intersection here so that our path is feasible both by the constraint of translational and angular acceleration. So now for a demo of where I am right now on the project. So right now I have a server which is able to do all of the calculations described from the path selection process, generating the splines, to the velocity profile generation, calculating a velocity profile for a given robot. And this server also exposes a basic API so it can be interacted with by a client. So I also wrote a client which allows me to input a spline. It uses the Quintic-Hermite interpolation with the derivative selection method that I described before to find a spline. And then I'm able to send this spline and a robot configuration to the server to calculate a velocity profile for it. Right now, it's just using a fixed robot configuration here. 8 units per second accelerations and decelerations, 8 units per second maximum velocity, and pi radians per second angular acceleration. So here, if I just input a basic spline, say 0, 0, 10, 10, 15, 0. So as you can see, pretty basic path here. I can actually update the headings here. Let's make this a little bit more interesting. Let's say that we're starting an angle of 120 degrees here. So I can calculate the velocity profile for this. My server will spit out a few things which I can graph. So first of all, we have the path itself right here, looks the same. Then we have the velocity versus time profile for the given robot. And then we have the angular velocity versus time profile following the same path. So you can see here the velocity versus time profile is always positive because we're always moving forwards, whereas the angular velocity versus time switches signs based on which direction the robot is turning along the path. So it looks like this profile this path would take about 6.2 seconds for a robot with that configuration to follow. So we start off with some acceleration. It's non-uniform acceleration, probably because there's some curvature constraints here at the beginning. We hit our maximum velocity, and we have to decelerate to be able to take this corner right here, presumably. And we accelerate again for the straight section, and then we decelerate here for this corner, and also because we need to reach 0 here at the end of the path. And the angular velocity also, you can see, stays here within the angular acceleration constraints, and also only reaches about less than pi radians per second in either direction. So very feasible to be followed by a robot. Another thing that's configurable here is the resolution at which we're calculating. Right now the resolution is set at 250, which means this path is being split into 250 segments, and then the whole velocity profile algorithm is being applied to those 250 segments. So now with trajectory calculation out of the way, the next step was to do optimization of path selection to minimize the time of the resultant trajectory. So I decided that my manipulations to the path selection that I would make would be changing the selections of first and second derivatives at the waypoints. Another possibility was to actually just move the waypoints and optimize the path based on the optimal movements of those waypoints, but I decided I wanted to keep the path as close to the original as possible, so only manipulate the first and second derivatives. And I knew that to evaluate the value of doing these manipulations, I wouldn't just be able to calculate the trajectory every single time, because that's a very expensive calculation. So I knew I'd have to develop some kind of cheaper heuristic to be able to evaluate these path selection changes. And to develop this heuristic, I'd have to look at possible relationships, correlations between path properties that are cheap and easy to calculate and resultant times of the trajectories. So also here, there is potential for using a reinforcement learning algorithm because you can have an actor whose actions are these manipulations to the first and second derivatives at the waypoints, and then your reward function is just based on this heuristic. So did the time get better, or did the estimated time get worse? And I look to use Q-learning for this because it's model free. It's more based on trial and error, which is more realistic for this scenario. So to develop the heuristic, I wanted to look at a few different spline properties. First of all, the arc length. This has an obvious relationship with the time to travel. The longer the path is, the longer the travel time is. Also, I tried looking at the mean magnitude of curvature multiplied by the arc length. So basically, which path has greater average curvature, but also accounting for how long the path is. Is there a relationship there between that and the time? And then the third thing I looked at is bending energy, which is often used to evaluate the smoothness of a curve or of a surface. And that basically is the integral of curvature squared with respect to arc length. And then the variable we're looking at, the changes to, the dependent variable, is the trajectory's time, where lower is better. We're trying to minimize the time. So I started off by generating a lot of random paths. I generated these short paths to have more diversity in the paths. I made sure that they were realistic for a specific robot configuration that I would develop the heuristic for. So I just kind of used a pretty standard robot configuration that's realistic for a mid-sized robot in the real world. And I made the distances between waypoints that were randomized, but I restricted them to a range that was realistic for that robot configuration. And also I restricted the heading changes along the path while I was randomly generating these paths. So here's some examples of the paths. Then I looked for these paths. I looked at the relationships between arc length and time. First of all, that was my first spline property, so that's graphed right here. There's a pretty clear relationship. It's actually more linear than I expected, seen as the relationship between distance and time on a straight line, at least, is a squared relationship, right? Z equals 1/2 AT squared. And then I looked at this mean curvature magnitude times arc length versus time. Also looked relatively linear, but I suspect this is mostly just due to the fact that they're multiplying by arc length. When I just graphed this one versus time, it didn't have much of a relationship, it seemed. So then I looked at bending energy versus time. This one also, definitely there is some kind of linear relationship here, not as strong though. So I decided to go with the arc length versus time, or sorry, the arc length and the bending energy as my two spline properties that I'd use to develop the heuristic. So I took these, the values of these and the values of the times, and used MATLAB's FitLM function, which finds a linear regression model for some variables and an output variable. So x1 here is the arc length, x2 is the bending energy, and then y is the time. And this is run on two different sets of 1,000 randomly generated paths. I ran two different sets just to confirm to myself that these numbers would be the same or similar, and they are. So you end up with this equation with this intercept and these coefficients here. The r squared on both of these is greater than 0.9, which is pretty promising. There's definitely, this is a relatively good model for estimating a time based on the arc length and bending energy. So going forwards, these linear models here would inform the heuristic. So basically, I'd be able to identify the arc length and bending energy of a generated path very quickly, very cheaply, and then get an estimated time. And as I make manipulations, compare the estimated times and use that to inform the reinforcement learning algorithm. So did the time go up? That's a bad thing. Did the time go down? That's a good thing. And train it like that. So that's where I am right now, and that's where I'm looking to go. So that's it. Here's some papers that I used.